morning to all. Sit down, please. So today's class we are going to see one of the important types of motion that we come across in our day-to-day life. Okay, let me give some examples for that. First one, you just consider the motion of the second hands of a clock. Okay, motion of the second hands of a clock. Okay, how it moves? What type of motion it is? Circular motion, yes, or it is rotatory motion, right? Okay. Another example, motion of planets around the sun. We are living in our mother planet Earth. Okay, Earth revolves around the sun in elliptical orbit. And what type of motion it is? That is also rotatory motion. And the third example I am giving, just to consider the vibration of the strings of a guitar. When we play the guitar, okay, how the strings of the guitar vibrates. Okay, so that is the third example. Now, the fourth example, motion of a swing. Motion of a swing. Now, consider these four examples. What is common in these four examples, or what is common in these four types of motion? Can anybody say what is common in four types of motion? That is the planetary motion, motion of second hands of a clock, okay, motion of a swing, and motion of the guitar string. What is common? Is the motion repeating? Is the motion repeating? Yes. Okay, we consider planetary motion. Earth rotates or revolves around the sun in 1 year, right? That motion repeats every 1 year. Okay, so that is a repeated motion. Like that, we take the motion of the swing. Swing also motion repeats, okay, along the same path at regular interval of time. And this type of motion only we are going to study here, and that is periodic motion. Okay, periodic motion. So we can define periodic motion. Periodic motion is a motion which repeats at regular interval of time. Okay. Again, now come back to the four examples. Take the two examples. For example, this motion of the second hands of the clock. Okay, the motion is periodic, you are seeing, and also motion of the swing. That's also periodic motion. These two motion similarities, that is both are periodic motion. Am I right? Yes. Is there any difference between these two motions? Can you find any difference between these two motions? So the two motions are periodic. Is there any difference? If we consider the motion of the swing, the object actually moves repeatedly along the same path, but it moves back and forth, or you can say to and fro. Okay, so this is periodic motion as well as this type of motion where the object moves to and fro or back and forth about a fixed point. That is called as oscillatory motion. Here, today we are going to see about oscillatory motion. One type of oscillatory motion, that is simple harmonic motion. Okay. Now we go to the video part.
Motion of the minute hand in a clock. Motion of the earth around the sun. What is common in these motions? The motion repeats after regular time intervals. The movement of the minute hand in a clock is periodic and its period is 60 seconds. The Earth takes approximately 365 days and 6 hours to revolve around the Sun. Thus, periodic motion is a motion which repeats itself after equal intervals of time. For example, a pendulum moving back and forth is said to execute a periodic motion. Our heartbeat is a periodic motion as it repeats approximately after every 0.86 seconds. A vibrating guitar string is a periodic motion. Observe the movement of a swing. This is an oscillatory motion. An oscillatory motion is one in which a body moves to and fro repeatedly about a mean or equilibrium position. Equilibrium or mean position is the position at which a body remains balanced as there are no forces acting on it. A body is said to vibrate or oscillate only when it possesses inertia so that it can move across the midpoint of its path. The frictional force acting on the body is minimal. There exists a force called restoring force that can accelerate the body towards its center.
Now we consider the oscillatory motion. So what are the reasons for oscillatory motion? Okay, when the body oscillates, once it starts from the mean position, it reaches an extreme position, right? Again it comes back to the mean position, and when it reaches the mean position, it overshoots in the other direction, goes towards the extreme position. What's the reason for this oscillatory motion? At the extreme position, when the body reaches, and this is a elastic body. For example, you consider a simple pendulum. Simple pendulum is a bob. It consists of a bob, that's a spherical body, which is suspended from a spring. Okay, it executes always oscillatory motion. And this bob is having elasticity, the property of elasticity. And because of elasticity, within the bob, force is developed. What is the force? Anybody can say? What the force developed? Due to elasticity, that is the restoring force, right? Restoring force. And this restoring force developed within the body always tries to bring the body back to the mean position. Okay? So at extreme position, the body comes back to the mean position is because of the restoring force. Now the body comes to the mean position. Once it reaches the mean position, the body repeats its motion towards other direction, right? And that is because of inertia. Okay, inertia, the property of inertia. Okay, it will continue the motion. Okay, it will not remain at the mean position, but due to the property of inertia only, the body now moves in the opposite direction. And again, it reaches the extreme position. Extreme position, which force is responsible? Restoring force. Okay, so we can say that the oscillatory motion is because of these two factors. That is, at the extreme position, restoring force brings the body back to the mean position, and at the mean position, the inertia overshoots the body to move in the other direction. Right? Okay.
All oscillatory motions are periodic motion, but all periodic motions need not be oscillatory motion.
So you have seen already two type examples, okay, periodic motion and oscillatory motion. Are all the periodic motion oscillatory? No, all the periodic motions are not oscillatory, but all the oscillatory motions are periodic. Right? Because if you consider a periodic motion like motion of planets around the sun, okay, though it is periodic, the body will never move to and fro. Okay, the motion to be oscillatory, what should be the nature of the motion? It should be back and forth or to and fro about the mean position. For this example, though the motion is periodic, the object is not moving back and forth. So we can say all the oscillatory motions are periodic, but all the periodic motions are not oscillatory. Okay.
One such example is the Earth's motion around the Sun. This is a periodic motion, but not oscillatory. A harmonic motion is an oscillatory motion which can be expressed in terms of a simple harmonic function such as sine or cosine function.
Now we see a particular type of oscillatory motion, what is called as simple harmonic motion. Okay, so what is SHM? SHM is a type of oscillatory motion, okay, where its displacement, okay, or the velocity of the object excluding SHM or acceleration can be represented as a sinusoidal function or cosine function. See the graph given here. Here you can see the red color graph. This represents a cosine sine wave. This is a sine wave and this is a cosine wave. Okay, this is a cosine wave. Now we can represent this is the graph representing variation of displacement of the particle with respect to time. So it can be either represented as a sinusoidal function or cosine function with respect to time. That type of motion is called as simple harmonic motion, right?
By simple harmonic motion, we mean a harmonic motion which is the simplest of all kinds of oscillatory motions. Thus, a body is said to execute a simple harmonic motion if it moves to and fro about a fixed point, that is, the equilibrium position under the action of a restoring force which is directly proportional to the displacement of the body. The restoring force is always directed towards the equilibrium position and hence is opposite to the displacement of the ball.
Now what we see is the definition for simple harmonic motion. When an oscillatory motion is said to be simple harmonic, that is, the restoring force developed in the body is directly proportional to the displacement of the body from the mean position. And what about the direction of the force? Always it is directed towards the mean position. Restoring force always tries to bring the body back to the mean position. Displacement is away from the mean position, but acceleration as well as the force acting on the body is towards the mean position. We want to indicate that force and displacement are opposite. So here in the equation they are given a negative sign. Okay, F is proportional to minus 5. Okay, yes.
Another example of simple harmonic motion is the oscillation of a tuning fork. The motion of the tuning fork and spring mass system exhibit linear simple harmonic motion as they occur under the restoring force. Observe a freely suspended magnet placed in a uniform magnetic field and oscillations of a torsion pendulum. These
Now you see, we have seen simple harmonic motion definition, right? And simple harmonic motions are of two types. That is, one is linear harmonic motion, another one is angular harmonic motion. Okay, linear harmonic motion means the displacement of the particle is linear. Example, spring mass system you consider. Okay, mass is suspended at the end of a spring and it is oscillated. How it moves? Along a line. Okay, or horizontal oscillation case also, it moves in a line. That's an example for what? Linear harmonic oscillation. Okay, and now we can see here what is this? This is an angular harmonic oscillation. That is, here you can see a magnet which is suspended from a fixed support and is made to oscillate between two poles. Okay, so what's the oscillation here? When it oscillates, it rotates about a fixed point. The string, okay, connected to the magnet rotates in an angle. So that angle theta is the measure of the displacement. That we call it as angular displacement, right? And next example what is given is torsional pendulum. Torsional pendulum also it consists of a disc-shaped object. Here it is given as a cylindrical object, right? It is suspended from a fixed support and is made to oscillate. Here also when the body oscillates, the displacement can be an angle one. That's angle. That's the suspension wire will twist. So the angle through which the suspension wire is getting twisted, that is the angular displacement. These are the two examples for angular harmonic motion, right?
motions exhibit angular simple harmonic motion as they occur under the restoring torque. Do you think all these simple harmonic motions are periodic? Consider a simple pendulum.
Now we will see, okay, related to simple harmonic motion, what are the terms? Okay, what are the terms related with the simple harmonic motion? Here you are going to see two different terms related with the simple harmonic motion, that is time period and frequency. Okay, so what is time period? Time taken by an oscillating body to complete one oscillation is called time period. And time period how you denote? That is denoted by the letter capital T. Okay. And next is frequency. What is frequency? Number of oscillations made by the body in 1 second is called as frequency. And frequency is denoted by the letter small f and its unit is hertz. Okay, these are two terms related with the simple harmonic motion. Okay, and let us see the video related to this.
Frequency and displacement in periodic motion. Have you ever observed the motion of the pendulum in a clock, or the motion of a clock's hands? Each of these bodies, that is, the pendulum and the hands, follow the same respective path over and over again with time. Even Earth revolves around the Sun along the same path repetitively after certain time intervals. This is also true of the Moon, which revolves around Earth. Such a motion which repeats itself in regular time intervals is called periodic motion. We will study the mathematical representation of periodic motion in this animation. Periodic motion repeats itself in regular or equal intervals of time. The smallest interval of time after which the motion is repeated is called the time period T of the periodic motion. We can observe that the second hand of a clock comes back to its initial position after 1 minute. Hence, the time period of the second hand is 1 minute. The time period of the minute hand is 1 hour. And for the hour hand, the time period is 12 hours. Earth undergoes two different periodic motions: rotation about its own axis and revolution around the Sun. The period of Earth's rotation around itself is about 24 hours, whereas for the revolutionary motion around the Sun, the period is about 1 year. Notice that as time period is a measurement of time, its SI unit is second. Instead of measuring the time taken by the motion to repeat itself, we can also measure the number of times the motion is repeated in a unit time. The number of times the periodic motion is repeated per unit time is called the frequency nu. Frequency is the reciprocal of the time period. Hence, its unit is per second. This unit is also called hertz, after Heinrich Hertz, the discoverer of radio waves. 1 hertz is equal to 1 oscillation per second.
Okay, so with this you are seeing what are the terms related with the simple harmonic motion, time period and frequency. Now we will go to the one of the examples for simple harmonic motion, that is simple pendulum. Okay, a simple pendulum, what is the construction? It consists of a small bar, okay, which is made up of a metal. Yes, and that is suspended from a fixed support, and that is made to oscillate. When it oscillates, it execute what type of motion? Oscillating motion or simple harmonic motion. Okay, now we'll see in detail about the simple pendulum in this video.
Simple pendulum. The pendulum clock was invented by the Dutch scientist Christian Huygens in the year 1656. This invention was based on the investigations of the famous scientist Galileo Galilei. Galileo studied the moving chandeliers in a church and found that their motion motion was periodic. This means that the chandeliers took the same amount of time for each oscillation. The pendulum clocks are based on this principle. The time-keeping element of a pendulum clock is a swinging weight known as pendulum. The pendulum swings back and forth, taking the same amount of time for each oscillation. Let us derive the expression for the time period of a simple pendulum. A simple pendulum consists of a ball of mass m suspended from the end of a massless, unstretchable string of length L. When the ball is displaced from the mean position and released, it starts oscillating about its mean position. Let us now analyze the two major forces acting on the simple pendulum. One of these major forces acting on the pendulum is the downward force due to gravity. The second major force is the tension exerted by the string. The tension is always directed towards the pivot point of the simple pendulum. We assume that there is no air resistance to the motion of the simple pendulum. When the ball is at its mean position, the downward force due to gravity is cancelled by the tension. When the string makes an angle theta with the vertical, the force due to gravity can be resolved into two components, the radial component and the tangential component. Since there is no motion along the length of the string, the radial component Fg cos theta is cancelled by the tension. However, the tangential component Fg sin theta is not balanced by any other force. This tangential component of gravity acts as the restoring force.
Now, you understood the diagram? So, when the pendulum is taken to one of the extreme positions, at the displaced position, what are the forces acting on the pendulum? And the gravitational force. So, what is done here is the gravitational force is absorbed into two components. One component is along the string in opposite direction, right? And that component is called as the radial component. Okay, what is the radial component? Fg cos theta. This is the radial component, Fg cos theta. And the other component is called as the tangential component, that is Fg sin theta. And here, if you see the radial component, Fg cos theta, that is balanced by the tension in the string, right? And the tangential component Fg sin theta is unbalanced. Am I right? Is there any force to oppose it? No. So this tangential component produces the necessary restoring force, okay, to move the pendulum, that is the body, towards the mean position. Okay, so that restoring force is given as Fg sin theta. Okay, so proceed with the derivation.
The restoring torque generated by the restoring force is given by the expression shown. The negative sign indicates that the restoring torque always acts to decrease the angle theta.
Okay, using this, when we calculate the time period of oscillation, okay, what's the formula we are getting is T is equal to 2 pi root of L bar G. Okay, L is the length of the pendulum, G is the acceleration due to gravity. And what are the factors on which time period depends? depends on the length as well as acceleration due to gravity. So how it depends on length? The time period is directly proportional to length of the pendulum and inversely proportional to acceleration due to gravity. Okay, these are called as law of length and the law of gravity. Okay, so now I'll conclude with this, and next we will go for the quiz. Okay. So this is the first question. Come here. At regular interval of time, if the motion repeats itself, then the motion is known as click tensor. Submit. Answer wrong. See for the solution. What is the correct answer?
Periodic motion.
Now go to the next question. The velocity of periodic motion is given by the equation. Girls, answer. Okay, what is the correct answer? We got the solution. Correct answer is omega into root of omega. Next question. Boys side, one of you come. When b equal to t by 2, omega equal to pi, then acceleration becomes. Correct. Okay, very good. Okay, this let me conclude. So what you have seen is periodic motion. Periodic motion, simple harmonic motion is one of the types of periodic motion, and with that we have seen what is the example. Simple harmonic motion example is simple pendulum, and time period of a simple pendulum we derived, and expression for time period. From that we have seen that what are the laws of simple pendulum, right? Okay, thank you.
Thank you.